Okay, and one more thing. The projects were officially due. They are still officially due. I will officially take them on that last day with no lateness penalties at all and hand them in at any point. But if you want a chance to do revisions, I'm really hoping they're in the folders there right now, or I get them before I leave the office today. If you give them to me at some point today, I will grade them furiously over the next 2 days, give them back to you Thursday, which gives you 5 days to do revisions if you want, okay? You can hand it in to me anytime, but if you want revisions, if you want a chance to revise, I need it before I leave the office today. Okay, so on page 30, like I said, we talk about a little bit more about math and art. We'll begin with number 1. Henry? Okay, so talking about not changing shapes or sizes of things. So for example, you could take one of your trapezoidal tables and move it right across to where one of the other trapezoidal tables is. Has it changed shape or size? No, that is called a rigid motion. It still looks exactly the same as it did. Maybe it's changed orientation. Maybe it's in a different place in space. Yes, if you break it, then it is no longer a rigid motion. Yes. But for example, if you were to take a circle and make it bigger, is that keeping its same size? No. So making a circle bigger is not a rigid motion. We're only going to be talking about rigid motions today. We'll go to Emma for in the plane. Zach? Okay, that's just some vocabulary. Let's dive into the actual, here's the kind of thing I might give you on the test. Go to Holly. Okay, so take a look at the triangle and some random point inside the triangle. And we're going to take that whole thing and reflect it over line M. That is to say, we're just doing a mirror image. So probably a bunch of you already can envision what the mirror image is without me saying anything. But if you need a push, mirror image, generally you take a point, you go perpendicular to the line, straight to the line, and then however far you went, you keep going the same distance. And then I'll call this guy right here B, and I'll put a little apostrophe. It's not the same B, but it's the new B. It's where B goes. So that point B has been reflected over the line. Can you guys go ahead and reflect the rest of the points in that picture over that same line, and then connect the dots to get a new triangle over here? Okay, any questions about reflecting points and drawing the new triangle? How are we doing on this one? Yeah. Yeah, so yeah, it's all eyeballing it actually. So we go straight to the line, and then you just estimate how far it is. You know, if you had a ruler, you could get a better estimate, but you want to make sure you're going perpendicular to the line. So I would send things more this way than that way. Okay, so we go straight. So this point looks like it's kind of far from the line. So however far it is, it's going to end up that far. So probably it's someplace down there. Okay. Okay. So check with your neighbor. If your picture is better than theirs, then help them out. So just look around, check in with your neighbor, see if it looks like a reasonable copy of the first triangle just flipped over. Okay, any questions about this reflection business? Just supposed to be rough? Yes. Just supposed to be a rough sketch, but I will probably ask you to reflect some stuff on the test. It's easier if it's on graph paper, so like then you can really count boxes. You'll have graph paper on the test. One little thing to note, if we are trying to read the letters of the original shape, I'm just going to arbitrarily pick clockwise to read them in. The letters are A, B, and D, right? Clockwise. What if I read the letters clockwise here? Again, start. So I said A, B, D. If we start here, A, D and B. So what happens to the order of the letters? They're reversed, right? Just one little note. When you reflect something, mirror image, things get reversed. You knew that. Whenever you look in a mirror, what are you looking at? Yourself. Things are reversed, yes? Like when you look in the mirror and you blink your right eye, it looks like your left eye in the mirror, because when you reflect, the orientation of things gets flipped. Okay, so that's reflections. Let's move on to number 4. We're back to Jocelyn. Okay, so rotations are oftentimes quite a bit trickier for people than reflections. So let's pause for this rotation business. All right, I've got point C. I'm going to rotate it by 90 degrees clockwise. Doesn't make sense to rotate unless I tell you what the center is. I'm telling you that the center in this case is A. So A is going to be fixed. Everything else in this picture is going to revolve around A. And to figure out, let's just look at point C. To figure out where C lands, what I'm going to do is draw a circle to help me. So here's the circle. I'm going to draw a circle with a center at A, and it goes through C. Everybody see that circle? So again, you're just eyeballing it. You don't have a compass, but if you did, you could draw a nice circle. So go ahead and draw roughly a circle centered at A that goes through point C. Okay, and so now what we're supposed to do is figure out where point C goes when I rotate it by 90 degrees counterclockwise. But C is going to stay on that circle, just going to find a new home somewhere else on the circle. So I want to go by 90 degrees counterclockwise. So look at the clock, make sure you know which way counterclockwise is. So we're going to sweep in this general direction, and we're going to sweep 90 degrees. If I sweep all the way around, do you know how many degrees I've gone? I've gone 360. So if I'm sweeping 90 degrees, then what fraction am I going? Just a quarter of the way, right? So you're going to take point C, it's currently there, you're going to swing it about a quarter of the way. I will eyeball and say someplace around here is my new point, C prime. And if you really want to see where that 90-degree angle is, like besides this quarter of the way business, if I connect A to the old C and A to the new C, if I've done things right, that should be 90 degrees. Maybe you guys have seen that little right angle mark before. And then you do exactly the same thing with B and D. Will B and D land on this circle? No, this is the circle for C only. So you're going to draw 2 more circles. B has its own circle, and so does D. So again, connect everything to A. Circle for D is quite big, might even go off the page at the bottom. And see if you can rotate by about 90 degrees counterclockwise. Same idea as before. All right, so rotation's a lot harder. Again, it's easier if you have graph paper. Probably next time I teach this, I'll just throw some graph paper on there. Just makes everything easier to sort of have a grounding underneath. Is D off the page? Yeah, so yeah, more workspace. Okay, so I've drawn my different colored circles up here so we can really see. We already did the blue point, C. I went ahead and drew B, rotated around about 90 degrees. And then D prime is maybe off the screen. And then we'll connect the new points. So there's B, and there's C, and there's D. And that triangle is supposed to be the original triangle, just rotated around. Okay, that's the hardest one. The last one is not the hardest one. The last one is going to be easier for us. And then once we finish the last one, we are going to see how these guys are used to create pretty pictures, things that look quite nice, quite symmetric to us. First, let's go to number 5, Blake. So if you rotate something by 360 degrees, what will it look like? It will be right back in the same spot. You won't even know it's moved unless you saw it like really rotate around. So what is the effect? No effect. Looks exactly the same. So if we had swept this triangle 360 degrees, it would have landed right back on itself. We didn't. We rotated it by only 90 degrees, so it didn't quite make its way all the way around the circle, just a quarter way. What's the effect of a 361 degree rotation? Yeah, it's the same as 1 degree. Okay, not really. I mean, like if you went 361 degrees, that would be a full revolution that you physically moved, but then just 1 degree is the like net result. Okay, we'll go to Sam for number 6 on the next page. Okay, 4 units right and 1 unit up. I'm just going to pick like a random point here. Let's just pick this guy right here. Random point. 4 units to the right and 1 up. 1, 2, 3, 4 to the right, 1 up lands me here. And then I'm going to draw that arrow. And that arrow is supposed to indicate exactly the same thing in words. 4 units to the right, 1 unit up. Okay? So what we're going to do is translate that triangle, everything in that triangle, by that arrow. 4 units to the right, 1 unit up. I'll do 1 point. You guys will do the other 2. If I take point C and I move it 4 units to the right, 1, 2, 3, 4 to the right, 1 up, and that's where it lands. C goes 4 units to the right, 1 up. And you guys go ahead and move B and D 4 units to the right, 1 up, and then draw the new triangle. Okay, how are we doing with the translation stuff? A lot easier than the rotation, right? Yeah, rotation's the toughest one. Okay, so we had the triangle, we shifted everything 4 to the right, 1 up, and it landed there. Ashley says, can we draw that arrow? Yeah, the purple arrow exists throughout the picture, right? That arrow is your guide. If you just take the arrow and apply it to everything in the original triangle, you'll find the new triangle. Okay, now we get to why we care about all this kind of stuff. We've talked about 3 rigid motions, 3 things that don't affect the shape or size of the object. We had reflections, we had rotations, and then finally these guys are the translations. Turns out there's one other one, it's called a glide reflection. We're not going to talk about it. Let's talk about 7. Alex. Okay, let's jump down to 8. It says we want to identify the kinds of symmetry that these 4 quilt squares have. So first thing we talked about today were reflections. So let's start drawing reflections. Let's draw lines in this picture. If I were to draw a vertical line right through the middle and ask you not to draw anything new, but to look at it and decide whether if you reflect the left-hand side, it lands perfectly on the right-hand side, and the right-hand side reflects and lands perfectly on the left. Does it? It does. It's pretty easy to see. Okay, this is actually part of the appeal of this kind of a shape. We really like things that look the same when you reflect them. So this has a, I'll say VL for a vertical line of reflection. Equally good, what other kind of line could we try? Let's try a horizontal line. Seems like going right through the middle is the place to try. If you reflect the stuff at the bottom over that line, does it land perfectly on what's already up there? It does. And the same thing, the top stuff flips perfectly and lands downstairs. So that picture also has a horizontal line of symmetry. Now, I don't want us to go around thinking that everything has these lines of reflectional symmetry. What kind of a line of symmetry do humans have, roughly? A vertical line or a horizontal line? Vertical. Roughly, we look the same to the left and right of a vertical line. It's not perfect, but it's pretty close. And if you had somebody that didn't look roughly the same left to right, you would think they looked quite strange. Okay, so we look roughly the same left to right. Do we look roughly the same over a horizontal line? No, we look really different reflected over a horizontal line, right? Okay, so this thing has those two lines. You know what? I'm feeling adventurous. Let's try a diagonal line. One vote for no. Few votes for no. Is that a yes or a yes vote for no? Yeah, the different colors represent different things. Yes.
The word symmetry and line of reflection be used interchangeably?
The line of reflection is a kind of symmetry. We're also going to talk about rotation symmetries. Yeah. Okay, so to tell whether or not this thing is the same reflected over, all right, let's take a look at this little triangle here. If I reflect it over that blue line, I'm feeling like I just get, you know, kind of that mirror image triangle right over there. Just flip it over. Do those two triangles look exactly the same? The answer is no, because of the colors, right? Because of the colors, they are not the same. So is that diagonal line a line of reflectional symmetry? The answer is no, right? It just doesn't work. Does everybody see that? It's not the same. Check the other diagonal line. Draw it in. Ask yourself if it's the same when you reflect. Does it work? No. Okay, so I feel like we're done with the reflections. We found two lines of reflectional symmetry. The next question to ask ourselves is about rotational symmetry. Can we take that object and rotate it and have it still look exactly the same? Well, it doesn't make sense to rotate something without a center. What is the natural point to choose as the center of rotation? Probably the middle of the picture. So let's imagine taking this picture and rotating it about that point. You guys have an advantage over me here. You could just take your packet and literally rotate it by, say, 90 degrees. Does it look exactly the same if you rotate it by 90 degrees? It doesn't. The colors have gone different. The arrows are probably pointing in different directions. All right, so 90 degrees doesn't work. Does everybody see that 90 degrees looks different? Okay, try rotating it by 180 degrees. And it looks exactly the same as when it started. So I guess we can say that 180 degrees is an angle of rotational symmetry. About 270. No, 270 is like 90. How about 360? Yeah, and in fact, it's silly, but we're always going to write 360 because it doesn't matter how it looks, it will always come back to itself after 360. Every object has what? Oh, yeah, every object has trivial symmetry. If you rotate by 360 degrees, it lands back on itself. Okay, we talked about reflections. How many lines of symmetry does it have? It has two, horizontal line, vertical line. We talked about rotations. How many angles of symmetry does it have? Two, 180 and 360. 360 counts. It's silly, but it counts. The last one we had was translations, like move the object 4 to the right and 1 up. Imagine physically picking this square up, moving it 4 feet to the right and 1 foot up. Will it look the same? You guys are looking at the object and saying it still has that basic pattern, but it looks different because it isn't there anymore. If it's up here, then it does not look the same as it looked before. The point of the symmetry is that you can't tell that it has done something. If you reflect this picture around the vertical line, can you tell that it's any different? No, that's why it's a line of symmetry. If you rotate it by 180 degrees, can you tell that something has happened? No, not unless you saw the person rotating it by 180 degrees. But if somebody picks it up and moves it 4 feet to the right and 1 foot up, can you tell that something has happened? Yes. It's not, there's no translation symmetry because if you pick something up and move it, it will look different. Almost all the time. We'll talk about some translational stuff on the next page. But for these guys, if you pick them up and move them, they look different. So there's no translation symmetry for this kind of thing. Okay, what I would like for you guys to do is analyze the 3 other quilt squares. So don't go on to the third one until you guys have all checked in with your neighbors on the second one. You're looking for all the lines of symmetry, all the angles of symmetry. Okay, so let's just come back together and double check our answers. The top right one, we have a vertical line for that and 360 only. Is that right? Okay, and the bottom left, we had no lines of symmetry, only rotation. 180 works, 360 works. And then finally this guy, horizontal line and only 360. Yes? Okay, a couple of observations. First one, why was 90 degrees a good thing to try rotating by?
It's a square.
Because it's a square, right? Okay, so there's something about the fact that this was a square that we decided we're going to try rotating by 90 degrees. We didn't try rotating by 80 degrees. What would it look like if you rotated by 80 degrees? Well, it wouldn't even land on itself anymore, right? It would be askew. It would be off a little bit. So we only rotated by 90, and then 180, and then 270, and finally 360. So here's the question. Suppose that it wasn't something so easy like a square, but rather was, say, a pentagon. The question is, what can you rotate this pentagon by so that it lands perfectly on itself? I want one point to land perfectly on the next one. If you rotate it, yeah, it's not 90 anymore, right? You rotate that by 90, it won't look like this anymore. So to find the correct angle, Charlie, what did you say?
Whatever 360 divided by 5.
Yeah, if you take 360, because it's 360 degrees in one complete rotation, and you divide it by the 5 sides of my pentagon, then we get 72 degrees. That's how much you need to rotate the pentagon by. If you rotate the pentagon by 72 degrees, it lands on itself. How would I figure out the next angle to rotate by after 72? Yeah, if we add another 72 to that, we get 144. If you add another 72 to that, we get 216. 72 on this, 288. And then one more 72. This is the part where you know you've done it right. You get 360 when you add another 72. Those are the 5 magic angles for a pentagon. For a square, it was 90, 180, 270, and 360. For a pentagon, it's those numbers. For a hexagon with 6 sides, it would be different still. But whatever it is, you take Charlie's magic formula here. 360 divided by however many sides. How many sides for the square? 4. 360 divided by 4 is 90. That's why it's 90. I mean, we just knew it was 90 because we have so much experience with squares, but that's the formula. 360 divided by number of sides. Okay. To find out what angles should you even try rotating by? What angles should we try to rotate by? Okay, next observation. How many lines of symmetry did this top left picture have? 2. How many angles of symmetry did it have? 2. Okay, so here's a picture with 2 of each. How many lines did the top right picture have? 1. How many angles? 1. There's a picture with 1 of each. Bottom left. How many lines? 0. How many angles? 2. Okay, that kind of broke the pattern I was looking for. Over here, how many lines? 1. And how many angles? 1. So here's something that turns out to be true. If you have some lines of symmetry, you're going to have exactly the same number of angles of symmetry. If you have some lines of symmetry, it's going to be the same number of angles of symmetry. If you tell me there's one line, like this bottom right, I can tell you there's only going to be one angle, 360. If you tell me, like in this top left picture, there are 2 lines of symmetry, guarantee you there's going to be 2 angles of symmetry as well. Always happens. What if I have some crazy picture in my mind? Some object with 10 lines of symmetry. How many angles of symmetry will it have? It's going to have 10. You don't even need to know what the picture looks like. As soon as it has 10 lines, it has 10 angles. And don't read too much into that. What if it has 10 angles? Can you say it has 10 lines? No, because of stuff like this bottom left picture. How many angles does it have? 2. How many lines does it have? 0. So it only goes the one direction. If it's got some lines, it's the same number of angles. It's possible it has no lines, but still some angles, okay? So let's see if we can give names to the 2 different kinds of things that we can have up here. Where are we now? Alex went, Justin, number 9.
Mathematicians have computation describe an object as n rotation. We classify the object as D.
Okay, if it's got both lines and angles, we're going to call it D. I don't know why it's D. Well, I kind of do know why it's D, but don't worry about why it's D. It is D if it has lines and angles of symmetry. Keep going, Justin.
If an object has n rotation, no reflection, we classify the object as D.
Okay, so if it has no lines of symmetry, it is a Z. If it's got lines, it's a D. If it's got no lines, it's a Z. To maybe help you keep these apart, which one of these, which letter, D or Z, has a line of symmetry? D does, right? You can draw a line right through the horizontal, right through the middle of D, and it has a line of symmetry. D are the ones with the lines of symmetry. Z has no line of symmetry. But if you rotated that Z by 180 degrees, what will it look like? It'll look like itself. Also 180, I think, right? If you like flip over, rotate your paper 180 degrees, I think that Z lands. Is it a backwards Z? I think it's a Z, isn't it? It's a Z. Yeah. Okay. So the one of these guys that has a line of symmetry goes with the lines of symmetry. The thing that has a 180 degree symmetry goes with the angles. So let's see if we can classify these guys up above. So this first picture has lines and angles. Does that make it a D or a Z? That is a D. Oh wait, this is a great moment to do some sign language stuff. Can Maggie? Can you show us the letter for D? Show. Everybody do that? D. Wonderful. And Z. What does Z look like? Okay, Z, you trace it out, make a Z. Okay, this way everybody can vote. This picture up here, it has lines and it has angles. Is it a D or is it a Z? Everybody hold up, we're voting. D or Z? Trace it out. This is a D. You guys need to work on your American Sign Language. So this is a D. So let's go ahead and call it a D. D. And it has a number that goes after it. The number that goes after it is the number of angles of symmetry that it has, which is 2. It has 2 angles of symmetry. Do not put a 4 there. That is not the total lines plus angles. We don't add lines and angles. It's just 2. How many angles? Look at the next picture. It has a line and it has an angle. Is it a D or is it a Z? D. With a line and an angle, it is a D. So let's call this guy D. Again, the number is how many angles it has. How many does it have? Just the one, the trivial one. That's D1, a single angle. So if it has lines and angles, then it's a D. When we go down here to this next picture, it has no lines. That makes it the other thing. Okay. So is this a D or a Z? This is a Z. Oh, you guys are better at the Z than the D. That's good. Okay, so this is a Z because it has no lines of symmetry. Z. And the number is how many angles of symmetry it has, which is 2. That is a Z2. And then finally, this has a line and an angle. Is it a D or a Z? That is a D. It has both. How many angles does it have? Just one. Don't say 2. Okay, so if I say classify a shape, guess what I mean? Z6, D4, tell me what it is, okay? Okay, let's go on to the next page. Okay, 10 for Doug. Okay, let's pause right there. Okay, Princess Bride, raise your hand if you've seen it. Okay, most of us. All right, so it says the Princess Bride. I'm going to take this thing and I'm going to just rotate it by 180 degrees. What does it say? It says the Princess Bride. Did we see it? I'll put it back. So rotate this guy by 180 degrees. It says Princess Bride. Is this a D or is this a Z? It has an angle of rotational symmetry. It has no lines of symmetry. Is that a D or is that a Z? It has only angles, no lines. Only angles is the Z. The stuff in the back is not quite symmetric, but it's close. So this right here is a Z. You can rotate by 180 degrees. You could always rotate by 360. So this is a Z2. That cover right there, Z2. You can rotate it by 180 degrees and it looks exactly the same. My wife got this for Christmas. I'm going to pass it around. You can just rotate it yourself. And then let's come back here to this other page. So here's a web page. There's a link that Doug just sort of got up to, and you can go to that link and click this thing that says create new ambigram. So the thing, oh, I don't know why it says my name. I actually haven't typed it in. That's creepy. I'm almost certain I didn't type. I haven't been to this website on this computer. That's weird. Yeah, this like I've got a profile online and it just knows. Like, okay, so here's the idea. If you have something like the Princess Bride cover where you can rotate it and it looks the same, it is called an ambigram. Ambi meaning 2. So 2 sides, 2 angles, you can look exactly the same. And so, some of these look better than others, but if you use your imagination, what does that say in there? It says Ian. And if I rotate it, it says Ian. That one doesn't look all that great, I'll be honest. Okay, who would like their name as an ambigram? Blake. Okay, let's take, who even said that? Was it Jocelyn? It wasn't Blake. All right, that's Blake. And Blake, that looks pretty good. That's an Ashley. So that's an ambigram of Blake. Let's try Ashley. Okay. And then I'll rotate. Ashley. Justin, all right, we'll try that. All right, so you guys can check these out later. Justin. Yeah, and Yeah, and this is actually quite common on tattoos for people. Like this is, I think, a tattoo website actually. Um, try what? Madonna. All right, so let's take a look at that one. ADA. All right, so it had trouble making it in the standard way, and so it made this kind of circular thing where I guess if you start in the right place, like maybe start right, well, it moves, of course, but presumably if you read around and it's kind of tough, it's an unusual, all the A's and the D's, it had some trouble with that. Um, yeah, so sometimes what would you like to try? Yeah. So one other thing you can do, Jocelyn. So one other thing you can do is you can type in like 2 words. All right, what does that say? Again, sometimes it works better than other times. So this is not an ambigram because it doesn't look the same when you rotate it, but still some people like their tattoo to be like, like their name in one direction and their sweetheart's name in the other direction, so you can play around with that if you'd like to. Okay, let's come back here. Okay, let's go to 11. Where are we now for 11? Is it, yes, 11. All right, does the circle have any lines of symmetry? If you reflect over that line, it looks the same. If you reflect over that line, it looks the same. Reflect over that line, reflect over that line, reflect over all of these. Okay, infinitely many lines, even more than 360, right? Infinitely many lines that you can flip over. How many angles can I rotate it and still have it look the same? Infinitely many of those. Not even just 1 degree and 2 degree, those work, but even half a degree works, and 0.7 degrees works. So is it a Z or a D because it has lines and angles? That is a D infinity. D infinity. When I was growing up in the Bronx, that was my tag. You ever see that on a subway car? D infinity. All right, let's take a look at an object with translational symmetry. Translational symmetry. All right, it's weird because it needs to look the same when you pick it up and move it. But of course, if you pick something up and move it, it's somewhere else, so it doesn't look the same. The only way for it to have translation symmetry is if it goes forever. So if, for example, you take this string of boring W's here, and you pick them up, and you move them to the left, and you plop it back down, if you move it to the right spot, it'll look exactly the same, right? Only because it goes forever. Okay, in practice, we never have stuff that goes forever like that, but we do have, like carpets. Like you guys have seen things like this picture right here, right? Like you've seen a lot of carpets that look like that. And if you take that thing and you pick it up and you slide it over and you put it down, it looks the same. And so here's an example of something that, if it went forever, would have translation symmetry. And again, we really like this kind of repeated pattern type thing because it looks the same. We like, just our mind really likes that kind of symmetry. So I would say that has translation symmetry. Okay, let's come down, symmetry, tiling. Okay, we're not going to talk about the tiling stuff. Let's move on to the next page. We'll just look at a few pictures. 17, Ashley. Sure, yeah. Okay, so tiling is just, you talk about tiling the floor with a bunch of tiles. It's just something that covers the floor completely and has no gaps and has no overlaps. You don't want one tile to be sitting on top of another tile. So here's a tiling of a floor using octagons, the 8-sided objects, and squares. And this is a pattern that you might have seen in some kitchen design or some bathroom design. There are a lot of patterns that you might see. You might see like a bunch of squares. For example, look up at, well, these are rectangles, but look up at the ceiling. This is a rectangular tiling, right? It covers the whole ceiling and there's no overlap. You don't have one tile sitting partially on another. So you can use rectangles to perfectly tile the ceiling. Could you use circles to tile the ceiling? We can't have, like, circles just don't fit into each other, which is why you won't see tilings with circles. You'll see rectangles. You'll see squares. You might see hexagons. You might see this picture here. If you're really artistic and mathematically inclined like this guy, you might decide you're not going to tile with rectangles or squares. You're going to tile with, say, birds and maybe fish. Okay, so I don't know, it's like really crazy that you've got like some black fish and some white fish and some black birds and some white birds, but it perfectly covers the ceiling, the floor, no overlap, no space, and Escher was a big fan of doing tilings, something like that. Let's go down to 18, Johannes. Okay, so it's the same kind of idea. I think this one was called Angels and Demons, and you can see the white angels and the black demons, and they tile the space completely. One thing though, how is that one different from the two up above? It does have some line symmetry. Jocelyn? Yeah, we can't move it and get the same result, right? Because for the octagons and squares, they're all the same size. Every octagon is the same size as every other octagon. But here you can see that the angels are different sizes and the demons are different sizes. And they get smaller and smaller as you get closer to the edge of this disc. So it is a tiling, but it doesn't have the nice translational symmetries that we talked about. Okay, let's go to 19. Kelly? Please. Okay, so next time you go to Subway and you order your sandwich, you're going to ask them for a tiling, or if you want to be fancy, a tessellation. You say, please tessellate my cheese. And then you won't have to deal with this unnecessary dairy overlap. You'll have life worth living, just like up above. Okay, so they'll tile it for you, covering everything, no overlap, and it's good. Okay, on the next page, you guys have 20 minutes, which I think is enough time if you're working, to go through the answers to this question. Again, you're going to work with your neighbors, but I want to be clear that you're doing what we want us to do. We got to do a lot for each picture. Let's read the directions first. Can we go to Iris? Okay, let's pause right there. So I'm asking you to do two things. You're going to be listing a bunch of stuff. You're going to say something like horizontal line of symmetry. Maybe there's a vertical line of symmetry. Maybe there's a diagonal line of symmetry. You're going to draw them, list them, and you're also going to talk about the angles. You're going to say, oh, it's got a 90-degree symmetry. It's got a 180-degree symmetry. You're going to list them, okay? So don't just say yes or two. I want you to actually list them. Show me the lines of symmetry. Write down the angles of symmetry. Iris? Okay, so 3 things you're doing for each. You're going to draw the lines of symmetry. You're going to write the angles of symmetry. You're going to classify the object with a D or a Z and a number. Okay, those are the directions for most of these. Check in with your neighbors and I'll walk around.